Okay, so this is the last class of module 1. Okay, so last 3 classes what we did is lesson 7, lesson 8 and this is lesson 9. So these are all informed searches. Okay, these are all informed search. Now in informed search we started with best first search. Okay, where the heuristic cost is simply Gn or Hn, whatever the node, the cost associated with the node. Okay, or the estimated cost from the goal. You can say here this is estimated distance from goal. So that is the only criteria how we are going to use best first search. Okay. Whereas in lesson 8 we discussed first A star algorithm, which says Gn plus Hn, where we can say Hn is the heuristic value of the node. Okay, that means distance from the goal, where Gn can determine the cost of the path. Okay, cost of the path. And improvement over A star is not improvement exactly. Another application of A star is AO star, where we see the problem in terms of and or graph. Okay. So as we saw here, you see, this is a typical problem statement for best first search, where you have only, you can call this Hn or Gn. Suppose let's call this Hn. Okay, the heuristic value of this node, which is distance from the goal, right? So this is actually the distance from the goal, or you can say the Manhattan distance, like this. This is the distance from the goal. Keep this in mind. In best first search, we have only this distance from the goal. Okay. Whereas, if you see here, the A star algorithm that we have, okay. This is the second example. Okay, first example we discussed. This is the second example, where if you see here, you have got, apart from, say, what is the distance of E from S? What is the distance of E from S? 1, 2, 3, 4, 5, or in this direction. 1, 2, 3, 4, 5, 6, 7. Right? So 7 is the, what is 7? 7 is the heuristic value of this node. Okay, 7 is the heuristic value of this node, and this 8 is the value of this path, It was 1 in the previous example. It was 1, so it was not written. So I think so. Cross check it. Okay. So that means for E, okay, for E, node E, if we say, suppose for node E, okay, if we say best first search, so what is the heuristic value? Fn. Fn for best first search. What is the heuristic value? Is 7. Right? Okay. Whereas for A star, the heuristic value is 7 plus 8, 15. Right? So for A star, the cost is Fn plus Gn, whereas For BFS, only the node cost or the heuristic cost will be there. Okay. Then AO star is utilized only to find the solution path in AND OR graphs, not for this type of problem. AO star is a different kind of algorithm which is based on A star but is applied to AND OR graphs. Okay. So two kinds of problem we have seen. One is, what is the first kind of problem? Shortest path. Shortest path problem. Right? Shortest path problem. Which one is this? This one is a shortest path problem. What is the second kind of problem we have seen? AND OR graphs. Right? For shortest path problem, we use best first search or A star, which is a special case of best first search, having the edge cost. The second kind of problem is AND OR graph, where the solution algorithm is AO star, where the solution algorithm is AO star. Now we will see the third kind of problem, which is known as Minimax. Okay. So in inform search, it's a huge topic. We have a complete course on this, I have told you, but we are focusing on only three kinds of problems. One is shortest path, the second one is AND OR graph, and the third one is Minimax. Okay. So from problem perspective, we have seen one is shortest path problem. Okay. The second one is AND OR graphs, and the third one is Minimax, which is Minimax. So all of you should say, so what is the algorithm that we have seen for shortest path? Informed algorithm. What are the algorithms? Last, what are the algorithms to solve shortest path that we have seen? Go last. What are the algorithms? What are the algorithms for shortest path problem that we have? Inform search. I mean, 7 a week inform search. This week is only inform search. Best first search. I would uninformed search. Now we are in informed search. Okay. So what are the two informed search algorithms? For shortest path problem, which informed search algorithms we have seen? There are so many. Which two we have seen? Gote hochi best first search. Hela. Seta ko mu lekhuchi. Eta ko mu lekhuchi BFS. Best first search. Hela. That is the first algorithm that we have seen. That is the informed search. What is the other algorithm? 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 A star. So what is the other algorithm? All of you. A star. Okay. So other algorithm is A star. So these are the two informed search algorithms. Okay. Now the same problem as you told can also be solved by breadth first search and depth first search also. Shortest path. But those are very inefficient. Very inefficient. And in fact, depth first may not even find the solution also. So uninformed. That was part in week 2. Week 2 re uninformed search. Best first, depth first. Third week re start karlo local search, which is hill climbing. So what is the problem with hill climbing? it gets stuck in the local minimum. It cannot explore beyond that. So therefore, we started with best first search, and an improved version of best first search is A star algorithm A star. Now the other kind of problem is AND or graphs. So what kind of algorithm we have used for solving this AND or graph? A star. Okay. So AND or graph ପାଇଁ algorithm होची A star, right? कौन AND or graph ପାଇଁ? Okay, so the last problem is Minimax, that we will see. So AND or graph is A star. Okay. Okay. So Minimax problems are part of a general problem known as board games. Like those are called zero sum games. So one wins, one loses. Okay, zero sum games. So two person, exactly two players, zero sum games. One player's gain is the other player's loss. The payoff is zero. Unlike reality, where the best solution is win-win. Everybody should win. That's possible. That means everybody should win in some way. Okay, but board games are only zero sum. Okay, there is no value of this. Complete information. Both players have access to all the information. They can see the board and thus know the options. Okay. When you play a board game, you have all the information about the board game. Alternative moves. Player takes turn to take their moves. Okay. Players take turn to make their moves. Okay. Maybe chess is one example. Game tree. So what is a game tree? A game is represented by a game tree. A game is represented by a game tree. It is a layer tree in which at each alternating level one or other types of player makes a choice. Layers of a game tree are min and max. Okay, so you have min max. Okay, so two players I have told you in the board game. One player is called max, the other player is called min. Okay, right? So to solve such game, you need the algorithm that we use is called Minimax. So for a complex game such as chess or checkers, search to termination is out of question. A good first move can be extracted by a procedure called Minimax. So good first move. So in many of the board games, the person who is making the first move, if he is making a proper move, then actually he will win the game. Okay, starting from the simplest one. Okay, this estimate can be made by applying a static evaluation function to the leaf node. Leaf node means the last node. We'll see that soon. Write down these two terms, max and min. Max is parent of min node is assigned the backup value equal to, okay, this thing will do it, then we'll understand. See, this is a typical game tree. So this is max, this is min, again this is max. So that means max, min means 2, 8, the minimum is 2. 4, 5, the minimum is 4. This is min layer, but this is max layer again. So max out of 4. Okay. So this is a typical Minimax procedure for game. Okay. You can go through it. The explanation is given here. Okay. So we back up from the bottom of the tree. From the bottom of the tree we back up, and then we decide the best move from the top. So Minimax is basically a depth first search from left to right. If you see here, like all of you, 5, 4. This is, what is this layer? This is mean. Mean max, mean max. Okay. In max, you have to take the max value of this 2. Right? So we start from left. 5, 4. Maximum is 5. Then suppose we put 5 here. Okay. We cannot because we have to go to the next. So it is 3. So we have to make it 3 because this is mean layer. Okay. Okay. So this pure Minimax procedure is clumsy because many of the, listen, pure Minimax procedure is lengthy because many of the paths we need not explore at all. Okay, those are unnecessary. That is what is given in this slide. Okay, so what is the goal of this Minimax procedure? The goal of the game tree search is to determine one move for max player that maximizes the guaranteed payout for a given game tree for max, regardless of what move mean will take. For the mean, it is the opposite. Okay. So the next concept in Minimax procedure is alpha beta pruning. Okay. So I told you Minimax is efficient because it will explore all the nodes in a depth first manner. Starting from the left side, it goes to the right, find out the minimum max like that. But we need not evaluate all these branches, okay, to the leaf node. So for that, we do one method known as alpha beta pruning. Okay. So in the exam, you might be asked to find out the alpha nodes and the beta nodes. Okay. So what are alpha and beta nodes? That we will see here. Okay. See this graph. Now, this is 4, this is 5. All of you, see here. सब देखा पड़े. एटी होती 4 और 5. सबको देखिए पे. पढ़े देखो. 4 और 5 अच्छ. So this is 4, right? Because it is a mean layer. So any value which will change it should be less than equal to 4, right? Similarly, here we have 1. Here we have 1. So the mean value is less than equal to 1 because this is the mean layer, right? This should be less than equal to 1. Now, in this mean layer, we have a value from here which is less than equal to 1, and here we have a value which is less than equal to 4. But here, it's a max layer. It should be greater than equal to 4. So that means this path can be totally pruned or totally thrown away, pruning. Because anyway, this should be always greater than equal to 4 because this is a max layer and this is 4. So this path we need not evaluate irrespective of what is available here. Okay. So that explanation is given in this slide. Okay. So what is known as beta cutoff? Okay. So you see here. Okay. First you need to write out what is alpha value and what is beta value. Okay. Beta value is the best value that the mean currently can guarantee. That means minimum value obtained so far is the beta value. Write down. Beta value is the minimum value obtained so far. That's the beta value. Write down. Otherwise you won't understand next. Beta value is the best value that mean can guarantee. That means minimum value obtained so far. Write this down. So beta value is the best value that mean currently can guarantee, which is the minimum value obtained so far. Similarly, alpha value you write the best value that max currently can guarantee. Alpha value is the best value that max can guarantee, that is the maximum value obtained so far. So the best value that max can guarantee, the maximum value obtained so far. So you have written alpha means max, beta means mean. Okay. Now we will see what is a beta cutoff, what is a alpha cutoff. Okay. Did you write, all of you? What are alpha and beta? Okay. Now we'll see what is a alpha cutoff. You see here, that equation you can understand easily, but you need to understand this. So in this case, we have a 8 here and we have a max. So it should always be greater than equal to 8. This should always be greater than equal to 8. But this is a mean node. This is a mean one. Okay. So it should be minimum. Okay. So here, what is alpha? What you have written in alpha? The maximum value that max node can guarantee. So here the maximum value that max node can guarantee for this is 8. So alpha is 8. Whereas if you go beyond that, the minimum value that the mean node can guarantee is 4 here. Okay, 4 here. Now, when the alpha value 8 is greater than the beta value, which is 4, you can cut this off, and that will be known as beta cutoff. Okay, that will be known as beta cutoff. So, what is the philosophy? The philosophy is that in the Minimax game, for example, in chess we see that certain moves you need not take at all, because that is not going to affect our final outcome. Okay, that I want. Similarly, what is alpha cutoff? So alpha cutoff, if you see here, alpha cutoff. So what is beta? Minimum value that the mean node, which is in this case 2. Okay. So if the beta n, which is 2, is less than alpha I, which is this max value, then we can cut this off. So this is alpha cutoff. Okay. Okay, so this is the bigger problem for alpha beta pruning, a large problem in a larger scale that you see. Now you solve this Minimax game. Hela, ita ko solve karo. Solve mane find out the value of the game. This one. Hela, ita dekhi ki solve karo. While I take attendance, you solve it. Pause. Okay. So what is the Minimax value of the game? Kete कहलो? 48. 8. Huge. Ita. Then list the horizon nodes, alpha beta cuts. Okay, alpha cut and beta cut. All these things you have to find out. Those two will take time. Okay, but at least you should find out the Minimax value of the game. Now let's see what is the answer. Yes. So first thing you have found out correctly, the Minimax value of the game, which is 48. Okay. Then you have to give some time to find out the alpha cuts. That means for finding out this 48, which branches are not required. You need not traverse at all. So those are alpha and beta cuts. Okay. So that you can find out after proper search. Okay. So that you do at home. Okay. So with this we complete this Minimax game and module 1. Next week onwards we will complete module 2.